Okay, so let's talk about concavity. So when we're dealing with concavity, we either are dealing with two situations. Something is either concave down or it is concave up. So in the most basic form, concave down looks like that, and concave up looks like that. When we think about this in terms of what it would mean for calculus, we have to think about it in terms of what would happen to the slope of our tangent line as we follow a curve that is concave down, or when we follow a curve that is concave up. So let's start by looking at what's going to happen to the slope of our tangent line around some sort of situation that's concave down. So let me just go ahead and add in an axis here. So that's my curve. It's concave down. It's always going to be concave down. So when I think about the slope of my tangent line following this curve, I see that from left to right, I have a really steep positive tangent line here. It's still quite steep. It gets a little less steep, even less steep, but still positive, flattens out to 0, then becomes less steep but negative, more negative because it's steeper, and even steeper when it is more negative. So we say when something's concave down, f prime of x is decreasing, okay? So our derivative following this curve, or the slope of all of our tangent lines around this curve, starts off really positive, goes to 0, and then gets more and more negative. So it's decreasing, okay? Think of it like this. These are all positive. This is still positive, but less positive, 0. This is a little negative, a little more negative, and really negative, okay? Meaning the size of my plus and minus signs here represents how negative or how positive those tangent lines are. So we can say that our derivative in this situation is decreasing, okay? When we deal with a situation when we're looking at a concave up curve, the opposite's going to happen. This situation, this tangent line right here is quite negative, okay? It's really steep, becomes less negative, goes to 0, becomes more positive, and even more positive. So we can say the slope, the value of the slope of this tangent line is very negative, whereas the value of the slope of this tangent line is negative, but not quite as negative. Here the value of that tangent line, or the slope of that tangent line is 0. Here the value of that slope of your tangent line, or the derivative, is positive. Here it's even steeper slope, so it's more positive, and here it's at its steepest slope, so it's the most positive. Okay, so when something is concave up, instead of saying our derivative is decreasing, we then say that our derivative is increasing. Okay, so those are the definitions of concavity. If something is concave down, your derivative's decreasing. If something's concave up, your derivative's increasing. Okay, obviously it needs to occur over a certain interval. Okay, you wouldn't say that very few graphs are actually concave down the entire time, but over a certain interval, when you have a piece of concave down, concavity facing downwards, you are decreasing, and over a certain interval, when your concavity is upwards, you are increasing, or your derivative is increasing. Okay, so let's go ahead now and look at a graph of a function, its derivative, and its second derivative. So we can say that this, I move it actually over to the side a little bit more. So we can say that this top function is y equals f of x, because that's our original function. The graph underneath it is its derivative, so y equals f prime of x, and the graph underneath the derivative is the second derivative. So y equals, I don't know, I put y prime, erase that. So y equals f double prime of x, okay? So all three of these graphs are related. Again, this is our function, our first derivative, and our second derivative curves. Okay, so let's just look at the curves and see what we notice right now. First of all, you should notice right away that in your original function, you have a maximum point here, a local max there, and a local min here, and those correspond to these zeros on your first derivative. And if you notice, at that point on your derivative, the derivative of the derivative equals 0, which corresponds to this point on your second derivative. Okay, so again, max gives you a 0, min gives you a 0, min gives you another 0. Okay? So we can see right away by looking at our original curve that we have some piece of concavity that's facing downwards and some piece of concavity that is facing upwards. Okay? The point where your concavity changes from being downwards to upwards is called your inflection point. So for this graph, I'm just going to estimate that this point right about somewhere in there, that is our inflection point, okay? So your inflection point is your change in concavity. Okay, so let's just look at this graph. So I know right away, let me get a different color. I don't want red, sorry, I just picked red again. Okay, so I know when I look at this curve in this area, right here, somewhere along this zone, you are concave down. Now I know from what I said before, if I'm concave down, my derivative is decreasing, okay? Now if I look at the graph of my derivative there, notice how it is decreasing in that region, okay, right? My derivative is going down my graph. It is literally a decreasing graph, okay? And notice how if my derivative here is decreasing, my second derivative is negative. Interesting, okay? And if I look at my curve when I'm concave up, okay, so in this region here, concave up, sorry, okay, I'll notice that my derivative right there is increasing, which means my second derivative right there is positive. So hopefully you noticed that this point, our inflection point, corresponds to the minimum of our first derivative, which, if you notice, corresponds to the 0 of our second derivative. So because of this relationship, because that when you're concave down and your derivative is decreasing, it creates a negative slope or a decreasing curve here, which creates a negative curve here. And when you're concave up, your derivative's increasing, which creates a positive slope here, which creates a positive line there. Hopefully you notice that at your inflection point, your second derivative changed signs. Okay, so testing for this change in signs, looking at where our second derivative is going to go from negative to positive or positive to negative, is what we refer to as the second derivative test. In class today, we talked about the first derivative test to find your maximum and minimums. Your second derivative test tells you where your inflection points occur, where that change in concavity occurs. So we can actually go through and formalize this, what is called the second derivative test, and that'll be our last thing for today. Okay, so the second derivative test, and again, it tests for concavity. So we can say that you're going to end up in two situations, okay? If your second derivative of x is greater than 0, for every value of x in some interval, then your original function, f of x, is concave up in that same interval. Okay? And the opposite, we can say that if your second derivative, f double prime of x, is less than 0, for all x, this symbol right here means for all, okay? For all x contained in a comma b, this symbol means in. Then f of x, your original function, is increasing. Oh, I'm sorry, I drew the wrong shape. Is less than 0, then you're concave down on AB, or in the interval AB. Okay, so again, I know this was a lot of information, and I know it's tricky manipulating these curves, but here, just to abbreviate, here's essentially what happened. Okay? When you are concave down, your derivative is decreasing. When you're concave up, your derivative is increasing, as we can see by our graphs, okay? Remember, when you were in Algebra 1, you were probably taught, like, put your pencil on the left-hand side of your graph as you draw along the curve. If your pencil's going down, it's decreasing. If your pencil's going up, it's increasing, okay? When I then realized that at this point, where my inflection happens, my change in concavity happens, becomes the minimum value of this curve. So then if I were to graph the derivative of this, I'd see, okay, well, I'm negative here, I'm decreasing, so my slope is negative here, which means I'm in a negative situation here. My slope of all my tangent lines here are positive, which means I'm in a positive situation here. Aha, fireworks. I wish I had like a firework thing, but I don't. So our inflection point matches our minimum, which matches our 0. Okay, and it can go the other way around. You can have an inflection point match a maximum, which would still match your 0. Okay, so whenever you're looking for any sort of change in concavity, you're looking for when your second derivative changes signs. Just like when you're looking for a max or a minimum, you're looking for the first derivative changing signs. When you talk about a change in concavity, you're talking about when your second derivative is going to change signs. Where's that point? Okay, we're going to do examples of this in class next time I see you, and there are some great examples in the reading I gave you tonight, so please read them and see if you can understand them. Do your very best to follow along with those examples. Okay?